Okay, welcome back. This is the 2016 VCE for the exam 1. This video will be about data analysis, core section, so we'll go through the questions here. Okay, so the blood pressure, low, normal, high, age under 50 years, 50 years or over, of 110 adults were recorded. Results are displayed in two-way frequency table. So the percentage of adults under 50 years of age, high blood pressure. So what do is we look for the column with under 50 years, high blood pressure, where they intersects 11, so 11 divided by the total, because we're looking for the amount of percentage of adults under 50 years of age. So the total is 58, so we do divided by 58 times 100. If you do that, you'll get 19% on your CAS. Okay, question 2. The variables blood pressure, low, normal, high, and age under 50 years or over are. Okay, so we know that this is categorical as this sum, and we know that it's ordinal because there's an order. It starts off from low, then normal, then high, so it's increasing. And then age, we also know that's categorical as categorical, and it is ordinal as well, because we do have some sort of order here. Okay, so as they're both ordinal, they both have orders, that'd be B, both ordinal variables. Okay, so question 3, the stem plot below displays 30 temperatures recorded at a weather station. So our key here is very important. It's saying that 2/2 is equal to 2.2 degrees. If you rush it, some might say 22 degrees, so just be careful of that. And it's asking for the mode here. So the mode by definition is the most frequently occurring number. If this is a chart such as a bar chart or histogram, then the mode would be the tallest peak in the graph. But here we have a stem and leaf plot, so we just look for the number that's occurred most. So by the looks of it, it's the 8s here. So 1, 2, 3, 4, 5, 6, that's the most occurring number. And remember, that's not 28, it's 2.8 degrees, so therefore the answer is A. The weights of male players in a basketball competition are approximately normally distributed with a mean of 78.6 kilograms. So our mean, this is the symbol for the mean, is 78.6 kilograms. Now this is the most important thing here. Normally distributed, whenever you see normally distributed, always think of this bell curve here shown. These are the percentages assigned to each standard deviation. So there's a standard deviation of 9.3 kilograms, which means each standard deviation. So for example, the first standard deviation here, I would add plus 9.3 to get to here, then plus another 9.3 to get to the second standard deviation, and so on. And if I want to go back one standard deviation, I take away 9.3 from the mean, and then I take another 9.3 away from the first standard deviation below the mean to get the second standard deviation below the mean. So this is how I draw this graph. Each graph has its own percentage. You might want to keep this in your notes. This is for everything. So the mean is in the middle here, and then on each side for the first standard deviation, it's 34% on the left, 34% on the right. They're symmetrical, which means all of this is 50%. And the rest is also 50% here as well to the middle mean. So keep that in mind. It's really important to have this in your notes. So now they're asking for the expected number of players in the competition with weights above 60. So now that we've got 60 here, this is 2 standard deviations below the mean. So if I wanted to calculate the number of players above 60 kilograms, well, I know that percentage. I know that this is 50%, so I've covered this, 50%. And then plus 34 plus 13.5 is 97.5%. So what I want to do is I want to do 0.975 times 456, which will give me 444.6, which rounded to closest is 445, therefore my answer is E. I've done 0.975 instead of doing 97.5 divided by 100, but the easiest way to write it in your calculator would just be 97.5 over 100 times 456, and that'll give you this answer when it's rounded closest to. Okay, so question 5. Brent and Sanjeeva both play in the basketball competition when the weights of all players in the competition are considered as the standardized weight of Z equals negative 0.96 and Sanjeeva has a standardized weight of Z equals negative 0.26. Which of the following statements is not true? So we're looking for false. So A, Brett and Sanjeeva are both below the mean weight for players in the basketball competition. This is true because they are below the mean weight because they have a standardized score which is Z of negative. Very important note, 0 when Z is equal to 0, this means this is the mean. So them having both negative values, Z scores, means they are below the mean. So that is wrong, so we can cross that one out. B, Sanjeeva weighs more than Brett. So if we look at it in terms of a number line here, this is also true because Sanjeeva has a weight of negative 0.26, for example. I know that's a standardized score, but if we just say in terms of weight, in terms of numbers, it'll make it a lot easier to understand. So negative 0.26 is greater than negative 0.96, which Brett has. So Brett has a less weight. He has less weight than Sanjeeva, as we can see on this number line here, which means this is true. So we're looking for something that's not true. So this is also wrong. Let's jump straight to D. Brett weighs more than 68 kilograms. So we have a very important formula here where Z, the standardized score, is equal to the number minus the mean divided by the standard deviation. So this is also very important to have in your notes. Because anything with standardized scores, you'll be using this formula. So here we want to know that if he weighs more than 68 kilograms, so we want to calculate the number. So we want to calculate X. And then from the previous question, it tells us here that there's a mean of 78.6 kilograms and 9.3 kilograms is the standard deviation. So we've substituted the 78.6 here and the 9.3 kilograms here, and we've solved for X. Menu 3-1, so menu solve, and X is given to us here. Weighs more than 68 kilograms. Brett's weight is 69 kilograms, therefore that's correct, so we crossed that one out. And then last thing, E, more than 50% of the players in the basketball competition weigh more than Sanjeeva. So this is true because if we think about it, Sanjeeva's weight is negative 0.26 kilograms, for example. So this is negative, so as we said before, the Z is equal to 0, so this is halfway here, the mean. More than 50% of players is this, so more than 50% is anything from here onwards. So that's obviously more than 50% here, as this is 50% plus an extra 50, plus the extra small percentage here. So yes, more than 50% of the players in the basketball competition weigh more than him. And then there's only one option left, which is C. So that's the answer. To calculate it, if Sanjeeva increases his weight by 2 kilograms, he would be above the mean weight for players in the basketball competition. So to calculate this, you want to find the Z score here of Sanjeeva, which is what we've done, like what we've done for Brett, and see and add 2 kilograms onto it. And if it's above 78.6 kilograms, that means that's true. However, this isn't correct if we were to calculate it, but because here I know that there's 4 things that are definitely wrong, C must be the answer. So what you want to do when you get questions like these is go through the most easiest things first. And usually, Vika like to put D or E as the answer for questions like these. So if you don't know the answer, the best thing to do is to guess D or E. But it's also a good method to just go and cross out each thing that you think is wrong. Okay, question 6. The histogram below shows the distribution of the number of billionaires per million people for 53 countries. So we have the histogram shown here. And using this histogram, the percentage of these 53 countries with less than 2 billionaires. So we're looking for less than 2. So immediately I'm looking at my scale here. Less than 2 is everything below here. So I'm looking for all of this. And we want the percentage of these 53 countries. So we know that the total is 53. So this is the total. And we want for less than 2 billionaires. So the total goes at the denominator, so 53 at the bottom. And the frequency for less than 2 billionaire here is 49. So I'm just looking at my graph, 49 divided by the total, and we want it as a percentage, which means times 100. And that gives you, doing it on your CAS, 92.45. And it's asking for closest to, and that's closest to D. Question 7. The histogram below shows a distribution of the number of billionaires per million people for the same 53 countries as in question 6, but this time plotted on a log 10 scale. So whenever I get these log 10 scales, the first thing I go and do is just put a 10 at the bottom of each number. Because this really confuses me personally, so I like to just have 10, so I know it's 10 to the power of. This thing here, log 10 number, can be really confusing. Some people might think log 10 of -4, log 10 of -3, so and so, so I usually don't like to look at that. All I know is that whenever there's a log, it's 10 to the power of the number on the scale. So don't get confused by what's written here, log 10 of number. It's not log 10 of -4. So, based on this histogram, the number of countries with 1 or more billionaires per million people is... So it's asking for with 1 or more. So what we know is 10 to the power of 0 is equal to 1. And 10 to the power of 1 is equal to 10. 10 to the power of -1 is equal to 0.1. So if you don't know that, you can do that on your CAS. It's pretty straightforward, but you should know that 10 to the power of 0 is just equal to 1. A million to the power of 0 is equal to 1. So keep that in mind. That's important to know. So now that we know we're looking for 1, we know that 10 to the power of 0 is 1. So we want to split our scale here. And we're looking with 1 or more. So our scale is here. We're looking for everything here. Rule our line with our rulers. That's 9. That's 1. Sorry, it's a bit better. 9 plus 1 is 10. I got that just by looking at the scale here. So E is our answer. Question 8. Parallel box plots would be an appropriate graphical tool to investigate the association between the monthly median rainfall in millimeters and the watt. So there's a really important table that you should have in your notes, and I'll have it here. Types of graphs. So basically, this shows where parallel box plots are appropriate to be used. So we can see here that in numerical, in the second row here, numerical categorical, where there's greater than 2 categories, parallel box plots are appropriate to use, as well as numerical and having categorical 2 categories only. So whenever we have a numerical value and a categorical value, we can use parallel box plots for that. So going back here, we want to look for something where we have numerical, and categorical. It could be 2 or more categories present. So what we have here is the association between the monthly rainfall in millimeters. So this is numerical because it's saying that it's the median rainfall in millimeters, and this is a continuous variable, numerical continuous. So we want to look for something that's categorical. So option A here, monthly median wind speed in kilometers per hour. This is numerical. We've already got something numerical, yes, so we need to find categorical, so that can't be right. Monthly median temperature in degrees Celsius, that's also numerical, so that can't be right. C, month of the year, January, February, March, etc. That could be an option. Monthly sunshine time in hours, that's numerical. Can't be that. Annual rainfall in millimeters, that's also numerical because numbers are involved. Can't be that, which means C has to be the answer. So what you want to do is you want to cross out the obvious answers first, cross them out so you know they're 100% wrong, and then go back to, you might have 2 options left and you want to choose the best answer from those. So make sure not to rush and go through everything first. Alright, question 9. Scatter plot below shows life expectancy in years, plot against HDI for a larger number of countries in 2011. Least squares line has been fitted to the data and the resulting residual plot is shown. Alright, so the equation of the least squares line is life expectancy equals 43 plus 0.422 times HDI. And the coefficient of determination is 0.875, so these are some important things. Should be highlighting. Let's go through the question here. Given the information above, which of the following statements is not true? So we're looking for something that's false. So, A, the value of the correlation coefficient is close to 0.94. This is wrong because it's true. Because the correlation coefficient is R. And it's asking us to find R. We have R squared. To find R, we find the square root of R squared, which is square root of 0.875. And that gives us 0.935. So when rounded, it's equal to 0.94. So therefore A is not wrong. A is wrong, because it's true. B, 12.5% of the variation in life expectancy is not explained by the variation in the HDI. So one thing really important here is, this is something else you should also have in your notes, is what I've boxed here in red. This sentence is really important because you'll get this a lot. And basically all you have to do is fill in the percentage and the y and x variables, and you'll be able to answer. So we know that y is the life expectancy because this is the response variable. Anything against this line here is y, and this is x. So you should be familiar with that. This is called the explanatory, EV, and this is the response variable. To fill in the percentage for this sentence, we use R squared. So we usually put R squared here, but we multiply it by 100 to make it a percentage, which means in this case it's 87.5% of the variation in Y, so life expectancy, can be explained by the variation in HDI. So that means if we substitute it into this sentence here in B, 12.5% is not explained. So if it's not explained, that means we need to do the opposite. So we do 100% minus 87.5 and we get 12.5%. So 12.5% of the variation life expectancy is not explained by the variation in the HDI, which is X. So that's wrong, we can cross that out. C, on average, life expectancy increases by 43 years for each 10-point increase in the HDI. So when it says increase here, one thing really important is that increasing is, whenever you hear increasing, you think of gradient. So if we look at the gradient here, it's 0.422. So for every 1 increase in HDI, life expectancy goes up by 0.422. So it doesn't increase by 43 years, because 43 years is the y-intercept. And that is not the gradient it's increasing by, because when we multiply it, HDI by 1, it increases by 0.422. When we multiply it by 2, it increases times 2. That's this number, 0.422. However, 43 is constant and it's not increasing, so therefore it can't be 43 years. It's actually increasing by 0.422. Now we're looking for something that's not true, so therefore C is the correct answer. But we'll go through D and E as well. D, ignoring any outliers, the association between life expectancy and the HDI can be described as strong, positive, and linear. So it's saying ignoring any outliers. So if we go to our graph here, if we ignore these outliers, do we have a strong, positive, linear relationship? So firstly, is it strong? Yeah, it's strong because data is packed together closely. So that's why it's strong. 2, is it linear? It's linear because you have a straight line. And another way to know if something is linear is to look at our residual plot, which they've given us here. And as we can see, the data here is scattered randomly. And because it's scattered randomly, that means we have a linear relationship. So that's something really important to note. Linear relationship means that the residual plot shows data randomly scattered. But if the residual plot shows some sort of pattern, for example, if I had a pattern that went up like this in the shape of a rainbow here, we can see a clear pattern here. And that means that we have a non-linear relationship because there is a certain pattern here. However, going back to what was there before, we actually have no clear pattern here. We've got everything scattered randomly. So therefore we have a linear relationship. So yes, it is linear. And last thing is it positive? So positive means, is it increasing? So if we have the line here showing us that it's increasing, as the X value increases, the EV, HDI increases, the life expectancy also increases. This is true because this is what's happening. So therefore we do have a strong linear and positive relationship. If the line was going like this, the data values followed this trend, that would be negative. So that's fairly easy and straightforward. Those 3 things you should keep in your notes. The strength, whether it's linear or not, and if it's positive or negative. So some important things to keep there. So it's saying here, ignoring any outliers, the association between life expectancy and HDI can be described yes as strong, yes as positive, and yes as linear. Therefore, this is true. So that's wrong because we're looking for something that's not true. Then E, using the least squares line to predict the life expectancy in a country with an HDI of 75 is an example of interpolation. So interpolation is a key definition you should have in your notes. Interpolation basically means if we use the regression line to make predictions within the original interval of data values used to obtain the equation, then the predictions are considered reliable. This is known as interpolation. So basically the number 75 here, if we look at the HDI on our graph, we find that 75 is actually within the original data set. So 75 is actually used here, which means this is inside the original data set, which means it's interpolation. However, if I had a number for, say, 110 has never been used to predict anything, and that lies outside the original data set. So 95 is my max, or whatever this last point here is. So 110 lies outside the original data set, and that's known as extrapolation. So that's important to note. And it's saying that 75 is interpolation. So yes, that's true because it's in the original data set. So that can't be right because it's true. Therefore, C is our answer. Alright, question 10. In 2011, life expectancy in Australia was 81.8 years. And the HDI was 92.9. When the least squares line is used to predict life expectancy in Australia, the residual is closest to. Okay, so for this question, we have a really important equation that we also need in our notes here, and that is the residual is equal to actual minus predicted. Now it's told us in the question that life expectancy in Australia was 81.8 years, and the Human Development Index was 92.9. So these values are actual. So that's an actual value. These are actual. When the least squares line is used to predict life expectancy, so we want to predict life expectancy, the residual is closest to. So we want to predict life expectancy, and we want to use this value because this is the only HDI value we have. So we say 43 plus 0.422 times the HDI, which is 92.9, because we want to predict life expectancy. If it said we want to predict HDI, then we use 81.8 years and we substitute it into here, and then we predict the HDI, but it's asking us to predict life expectancy. So we use the number for when we want to predict something, we don't substitute a number in there. So we need to fill in the gaps, so we'll fill in the gap for HDI, so 92.9. Do that on your calculator, and you should get 82.2038. Obviously don't need to write that value. This is the predicted, yeah, because we substitute it into the equation. So anything that we substitute into the equation, it's predicted. So now this is the predicted value. So predicted value. Now it's actually told us the actual here. So it says life expectancy was 81.8 years. Now we want to use this equation here, and we want to say, okay, so the residual is equal to the actual value, which is 81.8, minus the predicted value, which is 82.2038. Do that on your calculator, and you get negative 0.4038. B is the answer. Alright, question 11. Table below gives HDI and mean number of children per woman for 14 countries in 2007. Scatter plot the data shown. Okay, so firstly, when you see a table like this, what you want to go do is make sure you get your variables right. So this is obviously the EV, this is the RV, that's X, that's Y. That's the easiest way to put it on your calculator when you are typing these numbers. Call HDI X and children Y. Personally, I find it easier. If you don't want to, you can just write H defined as HDI and children when it's on your CAS. So it's saying the scatter plot is nonlinear. Log transformation applied to the variable children can be used to linearize. So it's saying that a log transformation is applied to Y. So log transformation. Okay, so we are changing Y. Now, it wants us to find the equation of the least squares line. Firstly, what I know is that children is the RV, or Y, is on the Y-axis. So when I'm looking for an equation, children must be on the left side. So that's the first thing I go and check. And I say, okay, well, children's here. Children is in A. Yep. B, C, D, E. That's all good. And HDI is on the X's, so that's all good as well. But it's saying that I have a log transformation here. So anything without a log is wrong. So log children, because remember I'm making a children transformation, yeah, to log children. So it can't be just children. So immediately B and D are wrong. Now I have A, C, and E, and just like that, I've eliminated two of my options. And then the next thing I look at is HDI. HDI must have no log next to it, so that's all good. Alright, now that I've got that, what I want to do is I want to go to my calculator, and I want to sketch, I want to apply this transformation. So I'm going to go show you guys how to do it now. Okay, so firstly, to sketch a graph like this, what we want to go to is this green button, list and spreadsheets. Click on that. Then we want to, you can either say HDI or children. Here, I'm just going to write X and Y, and you write that in the top in the very first row, so in A and B, write x and y. If you have another variable, put them in C and so on, which we will have. Then all you have to do is just plug in those numbers, so 27.3, and I'll do those and be right back. Okay, so I've just finished putting in all the numbers, as you can see here. I just wanted to say a couple of quick calculator tips that probably 99% of teachers won't teach at school. When you're at the bottom here, and you want to go up, you can press Control 7 and they'll go all the way up. Control 1 takes you all the way down again. So that's really important, just to go up and down anywhere on anything you're on. Control 7, if you're on one line here, Control 7 takes you to the back of the line, Control 1 to the front of the line, the row. So it's just a really good shortcut when you highlight stuff. Control 7 all the way to the top, Control 1 all the way back down. So there's some really useful calculator tips there. So now back to the question. Okay, so now that I've put all the numbers in, all you want to do is just go back, press on Data and Statistics, this purple app, open that up, and then obviously X goes at the bottom. That's how I remember it easily so I don't get confused. X at the bottom, Y on the side. Then you get this curve, which is very, very similar to what's here, what's shown you, and it should be the same. So we want to straighten this, and it's saying a log transformation is applying to children, so that's Y. So I want to go back, Control 7 to go all the way top. I want to call this Y2, and in this row where there's an equal button on the side, you want to write in log 10 of y. And see how y is bold there? That means it's defined. So I want to go ahead and press enter here. And it's going to say column reference. You want to go click on it, choose variable reference instead, press OK. And then you get all these numbers here. So basically, if you want to sketch the linearized graph, go back to Data and Statistics, and instead of y, go ahead and change it to y2. Hit enter, and you see how the line there's comes slightly more straight. Press menu 4, 6, 2, and over there it comes up with your linear regression line. Okay, so now our linear equation has come up, and we want to pick which one's the right one. So we have 1.05 as that's our A. So we have 21 here as our A. That can't be right, so the answer cannot be E. And then we have 8, can't be C as well. So it has to be A. So I'm using my left hand. So now we have 1.1, that's that value rounded there, and minus 0.0095, just as shown on the calculator here. So that's how you do it using the calculator. Very simple question. Question 12. There is a strong positive association between a country's HDI and its carbon dioxide emissions. From this information, it can be concluded that increasing a country's carbon dioxide emissions will increase the Human Development Index. So, everything here with questions like these, whenever it states will increase, it's wrong, because this is something that's definite, and this is saying there is a strong positive association. So I like to draw a quick graph like that. So basically HDI and CO2 emissions. So as HDI increases, CO2 emissions, but that doesn't mean it definitely will increase. So whenever you see will increase, just cross those out immediately. Those are definitely wrong. What you want to look for are things like tend to. Those words are more accurate, and those are the answers that are correct compared to will increase, because will increase is saying that as HDI increases, CO2 will definitely increase. However, there could be small peaks down So will increase straight away, cross it out, don't even think about it. Option C, this association must be a chance occurrence and can be safely ignored. That's a lot of rubbish. Countries that have higher human development, so higher human development index, indices tend to have higher levels of CO2 emissions. So yes, I believe this is the correct answer. Countries that have higher human development indices tend to have lower. No, it can't, because it's saying it's a positive association. Positive means it's going up. Therefore, E is wrong and D is the answer. Question 13. Consider the time series plot below. The pattern in the time series plot shown above is best described as having a irregular fluctuations, only increasing trend with irregular fluctuation, seasonality. Okay, so one thing to really consider here when looking at these is have a look at where the peak is for every peak, and for every cycle, consider where the highest point is and the lowest, and see if there's some sort of pattern and if they repeat. So for example here, the highest, see 1, 2, 3, 4, 5, and then here 1, 2, 3, 4. So there isn't really a cycle going on here because the highest and lowest peaks aren't really being repeated over the same period of time. So if we go to the multiple choice here, firstly it says, let's have a look at B, an increasing trend with irregular fluctuations. So does this look like it's increasing? It's sort of just staying constant. There isn't really an increase or decrease. So, and if we go to our definitions here, it says trend, tendency for values in time series to increase, decrease over a significant period of time. So as we can see here, there's an increasing trend or a decreasing trend. So we don't have any of those here. So I'll cross out B. Anything with increasing or decreasing is wrong. So that's already 3 of our options out of the way. So we've got 2 to go. So we can either have irregular fluctuations only or seasonality with irregular fluctuations. So if we go back to our notes, seasonality here describes data that has regular and predictable changes which repeat across a year or less, often matching actual seasons. Example, ice cream sales would predictably peak around summer months and dip around winter months. So here's an example of season. See, every winter here ice cream sales are at a low, and every summer they're at a high peak. So is this shown here? See it after every second, so 14 months, 26 months, 38 months. So as you can see, 2 months after 12 and 24, so essentially February, January, February, or February, March, there is a increase. There is a peak here with mean temperature. So yes, there is seasonality. So I would say seasonality with irregular fluctuations. It's not just irregular fluctuations. Irregular fluctuations just means that there's random peaks at random times throughout the year. So as we can see here, we can have a couple of irregular fluctuations here and there. So that's what irregular fluctuations means. So C is our answer. Question 14. Table below shows long-term average of number of meals served each day at a restaurant. Also shown is the daily seasonal index for Monday through to Friday. So we know that our seasonal index for Wednesday is 0.84. Just there. This tells us that on average the number of meals served on a Wednesday is 16% less than the daily average. Why? Because 1.0 is the average. Just like our mean, 1 is here, 0.84 is below the mean, which means it is 16% below. So here's our 0. 16% below the daily average. So, for example, Friday here would be 10% above the daily average. So that's the same here on Wednesday. We did 100 minus 84, so 100% minus 84%, because this is what the seasonal index means. So answer is A. Okay, for question 15, last Tuesday, 108 meals were served in the restaurant. The deseasonalized number of meals served last Tuesday was closest to. So this is another really important equation that we should have in our notes. Deseasonalized value equals the actual value divided by the seasonal index. Now this equation is going to help you answer this question. So if you don't know the equation, you can't answer the question. So basically it's asking us to find deseasonalized, so we don't know what that is. So deseasonalized. We know the actual value of meals served, and that was 108. As it says here, 108 meals were served, so that's the actual. Up here, don't get confused with this is the average. So it can't be 93. 93 is wrong, because this is the long-term average. We are wanting the actual number of meals served on Tuesday. And so we need the seasonal index as well. So the seasonal index for Tuesday is 0.71. So we just bring in 0.71. Do that on your calculator, and you will get 152.11, and it's asking for closest, so the answer is E. Okay, question 16, last question in data analysis. Seasonal index for Saturday is closest to what? So we don't know the seasonal index for Saturday, but we know the long-term average, and we've just got that from the table here, 190. To work it out, it's best to do it with ratios. So I like to work with ratios. It's very common in chemistry, but it's also a very good way to do further maths as well. So 190 for the average is a ratio. We're trying to find the ratio, what the seasonal index for that is. So we can choose any other day of the week. So you can either choose Monday, Wednesday, Thursday, Friday, anything that has given both the long-term average and the seasonal index. So choose either from Monday to Friday. We'll just go with Friday, which has a long-term average of 145 and a seasonal index of 1.10. All you have to do now is just cross multiply and see how you get an x here. You just multiply diagonally. So we say 145 times x is equal to 190 times 1.10. Solve for x and you get 1.44. The question is saying is closest to what? And that's closest to D. So that's the easiest way to work it out via ratios. We look for, we get our unknown, we set the ratio 119 to x because we want to find the seasonal index for the long-term average. That's why we put them together in ratios, and then we find another day of the week, and we say what the long-term average for that is and the seasonal index. Make sure when you're doing ratios to remember that the long-term average must be under each other. So everything must be together. So x, this is the column for seasonal index, and this is the column for averages. You can't do 190 to x and then say 1.10 to 145. That's not going to work. If you calculate it, it's not going to work. So each thing must have its column. So seasonal index and average. Remember the two dots in the middle as well. Cross multiply, and that's how you get your answer. So your answer is D, 1.45.